Hello and welcome back to Differentiation and Introduction. And I think we can wrap this up today. So in the previous video, we talked about how we cannot find the speed of a car just from a photograph because a photograph represents only one point in time. What you need is another point, right, in space and time where you can compare the distance traveled and the time taken. That's how you get speed. That's how you work out gradient. All right. And we also talk about the first principles of differentiation. That is the bedrock, the foundation of differentiation, okay, of this topic. And today in this video, we're going to go through an example on how to apply this first principle. Okay, but before that, I think I want to do a recap of what we learned so far. And what you see on the screen is on the left, we have in blue gradient, which I'm going to call rise over run or straight line gradient. That's what we learned before. And on the right, you see in green is what we're learning right now, differentiation using first principles. Now, comparing these two, I would like to look at some differences. First of all, I think the most obvious difference is the limitation of the straight line gradient. It can only be used on straight line graphs. But the green one, which is why we're learning it, it can be applied on any type of graphs. Any, okay? There are a few exceptions, but they are very rare. So you don't need to worry about it right now, okay? And the next difference I'm going to talk about is this. For straight line gradient, we actually get two pairs of coordinates. We substitute the numbers in and we get a numerical value for the gradient. But for differentiation, we don't do that. We actually use algebra. Algebra is much more powerful. By using the letter X, we can represent every single point on the graph. So it's like working out every single point without actually working out every single point, if you get what I mean, okay? And the last one is that for straight line gradient, the 2 points can be anywhere. You can put them near, you can put them far, it's fine. It will still give you the same gradient. But for differentiation, the 2 points have to be very, very close to each other, almost like there's no distance between them at all, okay? That's what we're going through so far. And now let's look at an example on how to apply first principles. What I did here was to choose a graph, and I've chosen x squared because x squared is a parabola. It's a simple equation, right? We can work with that. So looking at first principles again, this is the first principle of differentiation, taking the limit of f of x plus h minus f of x divided by h. So perhaps I would like to find out what is f of x plus h in this case when we have the graph x squared. Now, f of x plus h is telling me that the input is x plus h, right? X plus h, okay? Next, I need to know what this function does. What does this machine do? And over here, we can see that this machine, what it does is it gives you x squared. It takes the input and it squares it. So what I'm going to get for the output is a square of the input. See, this is my input. I'm going to square it. So this is our f of x plus h. Okay, next, I'm also interested in what's f of x. F of x is when I substitute the input as x. Oops, let me change to green. If I put in the input of x, then I'm going to square the input for the output. Okay, so that is my f of x plus h minus f of x. So you can see here in my first line of working, this is my f of x plus h. This is my f of x. And all this is divided by h. Okay? Easy. Now, in the next step, I'm going to expand this bracket over here. X plus h all squared. Okay? Now, you know this is an identity. This is the same as a plus b all squared, which will give you a squared plus 2ab plus b squared. Okay? Which is x squared plus 2xh plus h squared. Not to forget, we still have this minus x squared at the back. Okay, and there you go. This is what we get in the numerator. Okay, and then next, what I'm going to do is, if you notice in the numerator, we can simplify certain terms, and that is we can actually cancel this positive x squared with this negative x squared over here. And what I'm left with in the numerator now is just 2xh plus h squared all divided by h. And you might also notice that in the numerator, there's a h in every single term. So I'm going to divide throughout by h, okay, with the denominator. And that is okay because h, again, is not 0. Okay, this will not be okay if h is 0, but h is not 0, so we can divide throughout, no problem. And then what I'm left with, I have no more denominator, I'm just left with 2x plus h. So we're going to take the limit of 2x plus h as h approaches 0, which means to say, what is going to happen when h becomes really, really small, like 0.000000001? What is 2x plus 0.0000001? Well, it's as good as 2x. Yeah, it's as good as 2x. But wait a minute, what does this mean? The gradient is 2x? What do you mean by the gradient is 2x? Well, this is what I mean. Say you're interested in the gradient at x equals to 0 at this point here. So when x equals to 0, right, the gradient is going to be 2x, 2 times what x is. So since x is 0, is 2 times 0, the gradient is 0. And you can see it's quite accurate, right? The gradient at this point on the graph, indeed, is flat, it's 0. There's no gradient, right? Let's use another point. Let's say we use x equals to 1. So when x equals to 1, what is the gradient? The gradient is 2 times of x, whatever x is. So x is 1, so the gradient is 2. And if you look at x equals to 1, it does indeed look like the gradient is 2, kind of steep. Yes? And yeah, this is actually quite sneaky if you think about it, right? What we have over here, okay, if you realize, this is actually a function. Yes? Think about it. Excuse me. We actually have what we call a gradient function. Right? Why is it a gradient function? That is because what you're doing is you're substituting x equals to 0, and what you're getting out is the gradient is 0. Okay? And we substitute also x equals to 1, and you're getting the gradient is equals to 2. Okay? And this function behaves with the description 2x. Whatever input you put in is just going to multiply by 2. Okay? And if you haven't realized what's so sneaky about this is, I just spent the last 2 videos convincing you that to find gradient, you need 2 points. And over here, through the first principles of differentiation, you only need to substitute in 1 point to get the gradient. Now, I think this is a very beautiful piece of mathematics if you think about it this way. The first principle of differentiation gives you a gradient function. That is insanely beautiful. Okay, so over here, I did a small thing over here. I said that, oh, Newton is saying to Leibniz, you're a genius, and Leibniz says back, no, you are the genius. Okay, of course they didn't say that, they didn't get along, but this is extremely beautiful. And this is where I'm going to check off my last checkpoint on the checklist. It says finding gradient requires 2 points on the graph, right? No. If you know the first principle of differentiation, you only need 1 point. You are no longer bounded by the laws of nature that you need 2 points to find gradient. That's absolutely beautiful. One last thing that I want to talk about before I end the video, and that is this. If you realize, I've written a function over here, yeah, that is different from f of x. It's f apostrophe x. And how we read this is called f prime of x. Yeah, it is a notation for the gradient function. And I've come to the end of today's video. I enjoyed making this. I hope you enjoy watching. This is the end of the introduction. Moving on, we're going to talk about more techniques of differentiation, things that will be more useful to us on a day-to-day basis. So until then, hope to catch you on the flip-flop.